How's that? Good? Hey, everyone. Thank you so much for having me here today. It really is an honor to be here. My name is Tom, and today I want to talk to you about smartphones. But more specifically, I want to talk about how tools that grew up in the desktop era, things like Ember, Angular, React, how they can make the jump to the mobile future. And I think when people think about adapting apps to phones, they often focus on the more obvious differences. So, for example, things like the screen size, things like CPU performance, the different input devices, like a touch versus a click. But I think that the context in which a device is used is important too. So because phones can be used anywhere, there are very few assumptions that you can make, whether that's how attentive the user is or whether they even have an internet connection at all. So I recently started working at LinkedIn in December, and one thing that I'm reminded of working on a site like LinkedIn is it's a reminder of how truly global the web can be. In many cases, adapting to smartphones really means adapting to an entirely new set of users. For many people, their first computer is a smartphone, and that means millions, maybe even billions of people participating, coming online without ever owning a desktop computer. And the more global your app is, the more combinations of devices and networks that you'll have to deal with. So CPU power can range from a feature phone to a low-end smartphone to the latest iPhone that has CPU power comparable to a laptop computer. Network connectivity can also range from GPRS to gigabit fiber to not being there at all. Just ride the subway in New York. And of course, there's the fact that each device has a different browser with widely varying capabilities. And without careful design, it's really easy to optimize for one particular combination of these things at the expense of another. So let me give you an example of what I mean. So let's imagine these two scenarios. Okay, so user A, there on the left, user A has a very low-end smartphone with a CPU that easily overheats and flash storage that is so slow that it's borderline useless. And in fact, the flash drive is full, so it really is useless. Now, this person's data connection is quite slow, so they use a browser like Opera Mini, which uses a proxy to heavily compress all of the assets that it downloads before they even get to the phone. Now, in comparison, user B has a high-end phone with a CPU that rivals laptop computers, plenty of fast storage. The only problem is that, let's say this person is traveling internationally and they don't have a data plan. So while they sometimes have access to broadband internet when they're at their hotel, it's only when they're in range of that Wi-Fi network. So for user A, anything that requires a lot of JavaScript is probably not going to work at all. Even if they stopped using a proxying browser like Opera, the slow CPU and storage means that downloading and evaluating a bunch of JavaScript is going to take a long time no matter what. And getting reasonable load times probably means rendering on the server and keeping the file size of everything as small as possible. Now, for user B, we want to make it work more like a native application. We'd be willing to spend more time up front to load the entire app and as much data as possible if it meant that we could still use it when the phone was away from Wi-Fi. And this is a lot like how native apps work in the App Store, right? Once you install an app, you never think, well, if I tap the icon, it's not going to open, right? I can open my email app, and everything is there, and everything works, even if I don't have a network connection. And this user probably also has higher expectations of our app. It would probably be worth sending a little bit more code if it means that they get 60 frames per second scrolling, smooth animations, because their hardware can definitely handle it. Now, the problem is, historically, the more that we've tried to take advantage of high-end phones and fast networks, the worse we've made the experience for the majority of the world. So, what is the solution to this problem? I'll give you a hint. The initials are P and E. You guys have an idea? Physical education. Very good, physical education. What's the answer? Shout it out. That's right, panic and evacuate the building. Very good. No, the answer is supposed to be progressive enhancement. But one thing that's implicit in all the advice that I've ever gotten anyway about progressive enhancement is you're kind of supposed to do it yourself. It almost always means rendering your stuff on the server and then denying yourself the temptation of using too much JavaScript. Now, browsers have advanced at a remarkable rate over the last 10 years. And to me, it feels like the web has more momentum than ever before. Every new browser release brings so many new features. And despite all of this incredible innovation happening in browsers, from IndexedDB to web workers, to me, it doesn't feel like the day-to-day experience of using web apps has actually improved that much in the past, say, 3 or 4 years. So why don't these radical improvements that are happening in the browser, why don't they seem to be translating into radically improved web applications? And I would argue that the reason for that is because the cost of code is too damn high. Taking advantage of all of those new features in the browser just requires a lot of code. And native apps that work offline with beautiful user interfaces are hundreds of megabytes often. And that's not even factoring in the fact that the SDK that ships with the operating system provides a lot of that functionality. Just parsing and downloading JavaScript can turn some phones janky. And when you bundle all of your JavaScript into a single file, every byte really starts to count. And in turn, this sets up misaligned incentives, where libraries have to compete on file size rather than robustness. So how do they achieve these improbably small file sizes? Often, it's by persuading you that the old thing is unnecessarily complex, which is the cardinal sin in JavaScript. But they have seen through the BS and built something simple. And this emphasis on file size is what leads the JavaScript community to its simplicity fetish. When file size relies on simplicity, and speed relies on file size, and speed is paramount on the web, then we have to pretend that simple tools are the best tools, because what other choice do we have? It's rational. The only way to write an app that runs well on slower phones and slower networks is to ship less JavaScript. And too often, that comes at the expense of handling edge cases or allowing ourselves to build these higher-level abstractions. And as a community, we often feel like we can't build sophisticated solutions because eventually we start to collapse under our own page weight. And we've seen this play out several times now. More sophistication equals more code equals slower load times. So the time period from 2011 to 2017 can roughly be broken up into the Backbone era, the Angular era, and the React era. Now, this trio of eras is also sometimes referred to as the Ember era. And it's easy to become enamored with the simplicity of a tool. And that can lead us to underestimate the complexity of building modern web apps. So let's hop in the time machine and see how the simplicity fetish plays out. So in 2011, the cutting edge of web app technology was Backbone. And I remember talking to people, and they would say things like, I really love Backbone simplicity. I can clone the repo from GitHub, read the source code, and understand it all in an hour. But after building a big enough app, it would get slower and slower, and they would discover that just one model changing caused the entire app to re-render. And worse, no one on the team understood how the app works. But good news. Unlike the complexity of Backbone, where you have to listen for change events and manually re-render entire view hierarchies yourself, Angular is super simple, because you just set a property on your scope, and it updates the DOM automatically. But after building a big enough app, you discover that the entire thing is a single controller with 3 million lines of code. And each time Angular has to dirty check, it takes 5 minutes. And worse, no one understands how the app works. But good news, my friends. React solves this problem by being so much simpler than all of that Angular spaghetti. How does it do this? Well, it can be simpler because it's just the V in MVC. But after building a big enough app, you discover that actually you need more than the V in MVC. And all of a sudden, your React, Redux, Relay, Router, Reflux, MobX app weighs in at 7 megabytes, becoming the F in WTF. and no one understands how the Webpack config works. So Don Norman, who you may know as the author of The Design of Everyday Things, wrote this in an essay about security. He says, "The numerous incidents of defeating security measures prompts my cynical slogan: the more secure you make something, the less secure it becomes." Why? Because when security gets in the way, sensible, well-meaning, dedicated people develop hacks and workarounds to defeat that security. For example, if you have password rules that are really restrictive, people tend to just write it on a sticky note and stick it on their desk, which is not super secure. So I would like to offer the Tom Dale simplicity corollary. The simpler you make something, the less simple it becomes. Because when simplicity gets in the way, sensible, well-meaning, dedicated people develop hacks and workarounds to defeat your simplicity. So how do we break out of this local maxima? How do we write one app that can scale up and down across different devices and performance characteristics? And I think we can learn from native developers here, because they've had to tackle a similar problem. Different CPU architectures have different instruction sets. So if you write some assembly code for x86, for example, and then you want to run it on ARM, you're out of luck. You have to start over from scratch. And learning assembly for all of these architectures is a really big task. If this was how system software was written, there wouldn't be much cross-platform code at all. And introducing a new CPU architecture would be borderline impossible, because there'd be no way to bootstrap the ecosystem. But we figured out a long time ago that a compiler can take a higher level program and get it to run across all of these architectures. And if a new architecture comes along, you just have to update the compiler. You don't have to rewrite every app in existence. So here's an example using Clang and LLVM to compile C code to a new architecture that definitely didn't exist in the 1970s, WebAssembly. And best of all, the compiler can not only make our code run on different architectures, it can also use its knowledge of the performance characteristics and how they differ across these architectures to optimize the code differently for those particular characteristics. So this is from a paper where they said they were talking about optimizing GCC for ARM. And they said, finally, a new target-independent feature could be implemented to take into account certain specific features of the target. For example, to make advantage of speculation feature of Intel Itanium, which of course is dating the paper a little bit here, we have implemented its support in the instruction scheduler. So basically what they're just saying is based on the target, you can optimize, you can write certain optimizations that you wouldn't expect every developer to know by hand. And if there's one thing that I want you to take away from this talk, it's that modern web toolkits are transforming from being these libraries that you call into something that is more like a compiler. Except instead of compiling a higher level programming language into native code, they're compiling your higher level app into a highly optimized version. And eventually, this will mean building multiple versions of an app and delivering the most optimized version for that device. And this could be as simple as, say, delivering ES6 builds to newer browsers and a transpiled ES5 version for older browsers. Or it could be something like automatically transitioning between server-side rendering and client-side rendering based on detected network speed, for example. But most importantly, these tools can finally embrace complexity by decoupling it from file size. If we can shift the complexity to our build tools rather than these monolithic runtime libraries, we can eliminate this enormous pressure to be simple. Unfortunately, I don't have a lot of time with you today, but I wanted to highlight 3 things the teams behind React, Angular, and Ember are working on that, to me, demonstrate the trend of frameworks staying relevant by becoming compilers. So let's talk about React first. And specifically, I want to talk about a project called Prepack. Prepack is an open source tool from Facebook for optimizing JavaScript evaluation. Now, the Prepack website uses quite a bit of computer science terminology to explain what it's doing. It is a genuinely very exciting and very novel computer science problem that they're solving. But you don't need to understand terms like symbolic execution or heap serialization to understand why Prepack has the potential to be a critical tool for optimizing web apps. But to understand to understand Prepack, And to understand why it's cool, I think we should take a step back and understand how something like a bundle optimizer like rollup works. The way rollup works is by starting with an entry point file and analyzing which file it imports. For each of those files, it looks at what that file imports, and so on. And then once it's analyzed the entire graph, it builds a new JavaScript file that includes just the modules that were actually used. And this is an example from the Rollup website. They have a little interactive REPL that you can use to play with. So all of our modules are on the left, but then the final output is on the right. And you can see that's quite a difference. Everything that we've imported is inlined right into this output file. And the modules that are never imported are just completely excluded. And this gives us much smaller files by eliminating the things that we don't actually use. But it's not just modules. That's not just the level of granularity. Rollup can do some really smart things if it sees exports that are unused. So in this case, note that we've added this new class to animal.js, but our output on the right remains the same as before. Rollup is smart enough to not include the feral animal class, even though animal.js, the file, is imported, because no one asked for that specific export. And this kind of thing is possible because module syntax was specifically designed to be statically analyzable. And static analysis just means figuring out things about how a program will run without having to actually run it. And Rollup isn't running your code, it's just kind of scanning it to figure out what gets imported and what gets exported. And modules don't work inside something like a conditional. So if Rollup sees an import statement, it knows with 100% certainty that module is always needed. So that's Rollup. It uses static analysis to optimize file sizes without actually having to run any code. Now, fortuitously for me, you all just got a deep dive lesson on V8. So just as a brief recap, we'll look at how a modern JavaScript VM like V8 optimizes JavaScript. V8 can't help you with file size. By definition, it has to have downloaded a file before it can actually run it. But it can help with making your code run faster. So this is the high-level architecture of V8 that by now you'll be very familiar with. And the three major components are the parser, which turns your JavaScript source code into a data structure, the interpreter ignition, which evaluates the JavaScript, and turbofan, an optimizing compiler, which turns your JavaScript into optimized native code. And optimized code takes more memory and it takes more time to generate, but it can run at truly ridiculous speeds. And as your program executes, V8 keeps track of which parts of your code get run the most and how they run. Based on this information, it will ask turbofan to create optimized versions of the code that it thinks will help your app run faster. And V8's optimizations require running your program. That's a good thing, since V8 not being able to run JavaScript is probably a bug. But because it relies on how the program actually runs, you have to use the unoptimized code for at least a little while until V8 can start making some decisions. And that means that things will take a while to get really fast, and every user pays that cost, even though the end result is more or less the same for everyone that does it. So we have this tension between static analysis and dynamic analysis, where optimizations that use static analysis can be run at build time, making you pay the cost once, and then all of your users benefit. But static analysis can only get you so far, because you can only perform optimizations that you have 100% confidence will work. Because if a module might get used, for example, if it might get used, Rollup can't remove it. Because if it guesses wrong, your app breaks. So optimizations that use runtime analysis can collect information about how a program actually runs, so they don't have to guess. But requiring the program to run in order to optimize it is a bit of a catch-22. By definition, it means that the first run will be running unoptimized code. And that's the opposite of what we want on the web, where we want things to feel instant. So that's what makes prepack so cool. What it does is actually run your code. Similar to V8, it's an actual, honest-to-God JavaScript virtual machine. But rather than being designed to run apps, it runs your JavaScript as part of the build process. And then from the result of running your app, it reverse engineers a simplified version that is faster for the user's JavaScript VM to parse. And understanding prepack is a talk unto itself, And I personally am still trying to understand how the heck it works. But let's look at a few examples of what I mean by reverse engineering a simpler version. So imagine we're writing a library that prints the start date for DinosaurJS. And I create a new moment object, and I format it, and then I use that date in a string. So let's take a look at what happens if we take this code and run it through prepack. And what you'll see is that prepack has replaced all of that code with a single string literal. The final result is what I would have got if I actually ran the previous code in JavaScript. But now, instead of every user having to allocate a moment object, having to parse the date string, having to parse the formatting string, having to emit the requested string, and then do the string concatenation, which we learned is fraught with peril in JavaScript, we just have this simple string literal. And in fact, in this example, I can skip including and evaluating moment.js altogether, including all of that extra data that it needs for particular user locales. And that's a huge savings if all we're using moment for is generating this message about when DinosaurJS starts. So this is a pretty contrived example, obviously. By itself, it probably wouldn't make that much of a noticeable difference. But each of these small savings really starts to add up, especially in code bases the size of like Ember or Angular or React. And the good news is I hear some rumors that Jason Miller will be introducing a new library called prepack. It does everything prepack does in only 3 kilobytes of code. So let's take a look at Angular next. Angular bet early on TypeScript, which is a language that I personally am a really big fan of. And if you're not familiar with TypeScript, it's a superset of modern JavaScript, extended with type annotations. And those types make refactorings much easier, particularly as your project grows, and I speak from experience, as well as giving you incredibly rich autocomplete in your text editor. But to me, one of the most exciting and underappreciated reasons to try to introduce types into JavaScript is for the potential it has for using that type information to produce smaller minified builds. So let's look at a JavaScript minifier like uglify. And minifiers are really good at using their knowledge of JavaScript semantics to make changes that don't change the behavior at all. So in this example, we do something called mangling, where the variable fruit is renamed from fruit to O. And because a variable inside a function can't be accessed from anywhere outside that function, this is called lexical scope, then this is a totally safe change. It doesn't change the semantics of the code at all, it just changes the output, the representation. But let's change this example just a little bit. Instead of making fruit a string, we're going to make it an object with a name property. So you can see that even though the variable fruit still gets mangled, the property name stays the same. And that's savings that we're potentially leaving on the table. So uglify.js has a property mangling feature that you can optionally turn on. But unlike renaming variables, say, renaming properties can really break things because the outside world relies on those property names. The names of properties and methods on an object are effectively its public API. They're exposed to the outside world. Uglify.js has, so for example, rewriting this onClick property won't cause an error, right? If it changes the name, the element's onClick property, it won't cause an error, you won't get something in your console, it will just fail silently because the click handler never got installed. There's another example from this. This is an example using React, where you have this component, and things like the database are private. You can make guarantees that this thing will never be used outside this component, but there are other things that React itself relies on as part of the component's public API. They're meaningful to things like libraries, and you wouldn't want to be able to mangle something like that. So there's good news. Google has a project called Closure Compiler that already supports this kind of advanced compilation, this advanced minification for JavaScript. Unfortunately, it requires annotating all of your types with JS.comments and other weird Closure-specific configuration. Approximately 7 people on the planet outside of Google have actually got this working. So the Angular team released this really amazing tool called Sickle that translates a TypeScript project into the output format that Closure Compiler expects. So by taking this extra information that you have in TypeScript, and because Angular is also written in TypeScript, so they're all participating in the same world, Closure Compiler can do some shockingly advanced minification. As the README for Sickle says, the goal is to let you write TypeScript and Sickle handles massaging it into something that Clojure compiler understands. And I, for one, am really excited to see Googlers working on making the advanced stuff that Clojure compiler does, this very underappreciated power, more accessible to the broader world. I think having more people use Clojure compiler would actually make a very profound impact on the real-world day-to-day, experience of using the web, making it much faster. And even if they could integrate this into ng CLI by default, I think it would make this huge practical impact. All right, lastly, let's talk about Ember. And more specifically, I want to talk to you about Glimmer. Glimmer is the rendering engine in Ember, and we also extracted it in March and released it as a standalone library that you can use even outside of an Ember app. And when you think about the performance of a web UI library, a component library, let's call it, there are three major metrics that you want to look at. The first is, how long does it take the library to load? The fastest rendering library in the world probably wouldn't be worth it if it's like 50 megabytes, right? But file size alone is just a proxy for load time. Given two files with identical size, one may take longer to load than the other because it contains more complicated JavaScript. And this is the kind of thing that prepack is designed to optimize. The second question is, how long does it take to render a component for the first time, when you have to create brand new DOM elements for everything? And third, how long does it take to re-render a component, updating the existing DOM elements when just the data backing that component has changed? OK, who remembers this app? You guys remember this? This is the bane of my existence. This is Ryan Florence's DBmon demo app from ReactConf a couple years ago, which highlighted the benefits of React's virtual DOM. And for a while, it set off this frenzy of performance benchmarks. And it's all anyone was focused on. How quickly can you update so many components on the screen? But more recently, the community's focus has shifted to be more on initial load times as we all try to grapple with this problem of delivering better experiences on low-end phones and slow networks. And the tricky thing is trying to find this sweet spot that balances between optimizing the first render and optimizing subsequent re-renders. And fundamentally, this is just an issue of bookkeeping. The more bookkeeping you do in the initial render, that makes subsequent updates faster, the longer that initial render is going to take. So consider this React component that returns some JSX that has been marked up using like Bootstrap classes and DOM elements. So on initial render, virtual DOM nodes will be created for each element here. And that makes a lot of sense. These are, you can think of JSX as essentially being instructions for how to create the real DOM. But if a single prop changes and we have to re-render this component, we have to run the entire render function again. And that's quite a few allocations of virtual DOM objects, not to mention all the diffing that has to happen to reverse engineer what changed between the last render and this render. So this example is small enough that the performance cost is negligible, but you can imagine like a very large app or inside a loop with a long list, this kind of stuff can really start to add up. So the question is, can we do better? So Glimmer uses handlebars templates for its components, and these get compiled when you build your app. The question is, what do you compile this handlebars template into? And in Ember's history, the answer to this question has changed 3 times. First, we compiled into JavaScript that concatenated strings, then compiled into JavaScript that built DOM. And now with Glimmer, we've tried an approach where we thought we could balance the fast initial rendering of JSX while improving on update performance. And we did it by treating handlebars, and in fact, the entire rendering pipeline, like a programming language. And we treated Glimmer like a virtual machine that runs that compiled programming language. So with Glimmer, we compile the template that you just saw into a JSON object that looks like this. Now, this probably looks like gobbledygook to you, but what this object represents is actually a sequence of opcodes or instructions that tell the Glimmer VM how to build a DOM structure. And we represent the opcodes in this compact data structure of arrays, integers, string literals. So parsing is super fast because you can use the JSON parser instead of the full-blown JavaScript parser. And memory consumption is much lower versus, say, compiling JavaScript. So when we landed Glimmer in Ember 2.10, many apps found that their template size dropped 70 to 80%, which is very significant. And we use integers to represent these instructions. This is both for compactness and also because it unlocks a few optimizations in JavaScript VMs like V8. But if we were to represent this in a totally hypothetical assembly language, it might look like this, kind of like a linearized set of instructions. And then we take those instructions and we run them on top of the Glimmer VM. So to build our DOM, let's take a look at what this looks like evaluating that program. To build the DOM, we iterate over this linearized set of instructions, each one building up a bit of the element. So first one is like open, which will create a new li tag, a new li element. Then we're going to execute this static adder opcode. Then we'll have another static opcode for the class. And then finally, we say flush element, which tells Glimmer, OK, this element is done. It's ready to be put into the DOM. So this is a pretty easy example, but it's completely static, right? What about something that has dynamic content? What I haven't mentioned yet is that the Glimmer VM is actually made up of two VMs. One is optimized for constructing and appending DOM elements, and the other is optimized for updates. So this is the program for initially rendering this template. Now, we could run this program again every time it updated, but you can see that there's really no point in spending time executing opcodes for static content that hasn't changed. So we can use a technique called partial evaluation to generate the updating program as the initial rendering program is being run. Essentially, operations in the initial rendering program are responsible for generating the opcodes to update themselves should the underlying data ever change. So let's take a look at what that looks like. So this is our initial program along the top. We're going to start running this on the VM again. We have this instruction pointer that tracks where we are in the program. So we're going to open the div. We're going to add a static attribute again. But now, this time, we're going to add some dynamic content. We're saying pull the value from person.firstname and put that as a text node into the DOM. And at the same time, that code, that opcode, in addition to updating the DOM, also has now generated the first opcode in our updating program. Now we get to flush element, which again puts it into the DOM, and now we're done. Now what's cool about this is that because there's a single piece of dynamic content in our template, we only have to perform a single operation to update it. And that means diffing a single value rather than having to allocate all this virtual DOM objects and perform a tree diffing algorithm. And what's neat about this is you can imagine why it's quite fast, right? Instead of having to diff the DOM, it's just comparing these two values. It's a little bit more complex than this, but this gives you a representation of what's happening under the hood. You're diffing values instead of DOM. And we noticed that when we were measuring the performance of this, basically all benchmarks only test pure dynamic content. But that's not actually representative of most apps in the real world, where you have plenty of divs and other semantic markup. So when we created a benchmark that had a mix of both, initial rendering for templates running on Glimmer VM was basically neck and neck with virtual DOM-based libraries. Now, I'm not going to put names here. I'm not trying to make it a competition. The important thing I want to show is that this approach is basically in the same ballpark as the virtual DOM for initial renders. But when you move to measuring updating performance, we were very happy to see that generating these optimized updating programs seems to have a big difference when it comes to updating and re-rendering. So today we've talked about 3 popular frameworks and some of the things that they're doing to improve performance on mobile devices. It's important to understand that modern frameworks are becoming optimizing compilers. They're not just something that you drop into a page with a script tag. And I think this is just the beginning. There's this really exciting trend towards sophisticated tools that can analyze your app, perform optimizations that would be time-consuming, if not practically impossible for you to do yourself. And best of all, code that clearly conveys that intent to humans has a funny way of being able to convey intent to optimizers as well. So in 2017, the idea that build tools are optional, I think, is totally outdated. A sophisticated build process is, ironically, the backbone of a modern web app. This morning, we've seen a bunch of, and in this conference today, we're going to see a bunch of techniques about measuring and improving the performance of web apps. And that's really great information. It's really great we have conferences to share performance information like this. But not everyone can have someone standing over their shoulder who's an expert, reminding them and guiding them. And I think baking it into these tools is very important. And I'm incredibly excited about a community that builds those tools to help democratize and commoditize performance know-how. The best part of approaching frameworks as compilers isn't just that they help today's apps become accessible to more people. By reducing the cost of code, we can build better apps that don't collapse under the weight of their own complexity. And by reducing the cost of code, we can finally dispense with an idea that I hate, which is that developer happiness and user happiness are somehow inherently in tension. This is a really exciting time to be a JavaScript developer. I, for one, am looking forward to web apps that load instantly, work offline, and feel great to use for everyone. Thank you.
Hi.
Hey.
I have so many notes, but not enough time.
Oh, God.
So like 4 years ago, I was working at the NBA on the stats website.
I remember.
And, yeah,
Angular app.
Angular app, right. I guess the problem there is we were live updating the basketball stats in real time, and we would have just like millions of people over the world just looking at the site, tons of watchers, site would crash within like 5 minutes, like all the time. And I remember being in an IRC chat with Brian Ford, who's on the Angular team at the time, and I was like, Brian, you need to help me here, you know? And it just like, we just weren't at like that time where like we can do that sort of thing, you know? And now it's like a trivial thing to do, have things updating really quickly. So I think that back then, I guess like the framework wars felt like a war. People were much more angry about whether you were using a certain framework or not. And now we're seeing, I guess, like more collaboration and like thought leadership between all of them, which is like really nice to see. Yeah. What do you think is going to be the next problem that modern framework communities have to solve?
That's a great question, because I was thinking about this the other day, where every time I feel like I'm starting to get like bored of framework wars, where it's the same crap, like, you know, same day, different, whatever. Something happens, and I'm like, oh, this just got so interesting again. And every time it feels like maybe you've hit like the state of the art, something always comes along. And I think there's so many interesting confluences of things happening right now. So in particular, there's like service workers, I think people are pretty hyped about that. The ability to truly architect web applications like native apps. I think you could see it coming a few years ago, but it wasn't real yet, and now it really starts to feel like, you know what, this is actually really real. But I think there's a confluence of that plus things like web workers and WebAssembly, so I showed one of the slides with the compiled Glimmer opcodes, and it's a JSON data structure, but one thing that we're planning to do probably within the year is convert that to a binary data structure. So there's actually no parsing step at all. It would just be like download the binary blob, throw it into typed arrays, and then there's no parsing cost at all. And then perhaps even more excitingly, I think we could probably get away with eventually being able to write Glimmer VM in a language like C or Rust compiled into WebAssembly. And then like the whole kernel rendering your app would be this like very optimized low-level stuff, but still allowing you to express your app with these like high-level nice languages like JavaScript. I don't know, there's so much cool stuff.
Yeah, it's really exciting, and it, you know, it can be overwhelming. I always tell people when they're deciding what frameworks to use, I'm like, just follow all of the modern ones and see like what they're working on, because you really see how web development is evolving, which I'm particularly interested in because now I work in tooling. But like, I don't know, it's just like really interesting to see.
Yeah,
like,
and I love the collaborative vibe too. Like I love talking with people from all these teams. I think we all get along really well, despite occasional Twitter flare-ups. Everyone's very open, and it just feels very collegiate, which is nice.
That's awesome. Yeah, so thank you.
Thanks, Jen.